Lambdas as first-class citizens. In this section, we're going to take a look at what it means to be a first-class citizen, how Lambdas replace old Standard Library utilities, templates and Lambda expression, type erasure for Lambdas as std function, and higher-order functions. Let's begin with video 5.1. Lambdas, versatile tools. In this video, we're going to take a look at the meaning of first-class citizen and the utilities provided by the standard libraries, which are replaced by Lambdas. This is a quote from Wikipedia, first-class citizen. In programming language design, a first-class citizen in a given programming language is an entity which supports all the operations generally available to other entities. These operations typically include being passed as an argument, returned from a function, modified and assigned to a variable. In C++, regular functions are not first-class citizens. As an example here, you're not allowed to define a function inside another function. Instead, if you use a lambda, you're able to do it and assign it to a variable. Here's an example of invoking the std findIf algorithm by passing a regular function. In this case, I have a bool function called predicate, which takes a const foo_ref. I can safely pass it to std findIf and it will work, but not because a function can be passed around, but because predicate is equivalent to ampersand predicate. It will implicitly be converted to a function pointer to predicate. Also, pointer to functions can be invoked with the call operator, so the internal implementation of findIf will seamlessly work for function pointers and/or function objects. As soon as you have something slightly more complicated, such as an overload set called predicate, with an overload that takes a const foo and an overload that takes a const bar, your code will fail to compile. In this case, trying to pass predicate to the findIf algorithm is now ambiguous, because this will try to implicitly convert predicate to a function pointer, but won't know what overload to take. Do you want the foo overload or do you want the bar overload? And the compiler is not able to deduce this from the invocation of findIf. You will have to explicitly choose the overload. As an example, you can use static cast to a pointer that returns bool and takes a const foo of predicate in order to disambiguate this predicate call. Let's now see what happens if you use a generic lambda. In this case, I can simply define a predicate lambda that takes a const autoref, and it will compile and work as intended with findIf, and it will take any type that is valid for the body of the lambda. This is valid because predicate is not a function pointer anymore, but it is an instance of a function object, which provides a templated operator call. Closures produced by lambda expressions are therefore first-class citizens. They can be used like any other object in C++, and they can be used as first-class stateless functions or more flexible stateful function objects. If you compare closures to functions or member functions, you'll see that they are way easier to work with in the context of generic programming or when having other functions that accept closures or function objects as arguments. Let's now take a look at some deprecated or discouraged standard library utilities that are replaced by lambdas. Many utilities in the functional header were deprecated in C++ 11 and removed in C++ 17. Here are some examples taken from CPP reference. There were some classes called unary function and binary function that were some adapters completely deprecated in 11 and removed in 17. Also, there were some binders, such as binder first and binder second, or bind first and bind second, that were used to bind one of the arguments to the aforementioned unary or binary functions, and these were, again, deprecated in 11 and removed in 17. If you have these in your code base, I strongly recommend you to find them and replace them with lambdas. There also are way more deprecated objects or adapters. As an example, we have pointer to unary function, pointer to binary function, pointer fun, memfunt, and memfun, and memfunref. All of these were replaced by modern utilities in C++ 11 and should be replaced by the superior solutions implemented using lambdas. Let's now see an example of how you can use a lambda to reproduce the behavior of these deprecated functions in a better way. So, above I have a auto b0 equals std bind first f with 42, which basically binds 42 as the first argument of the f function call, and that's deprecated, and you should not use this function and replace all current occurrences in your codebase. The recommended way is to create a generic variadic lambda that takes any amount of arguments by forwarding reference and then invokes f, passing 42 as the first argument and forwarding everything else as the rest of the arguments. While this is unfortunately way more verbose than bind first, it's also way more flexible, and the compiler can transparently see what you're trying to do and aggressively optimize or inline your binding. While in the first case, by using std bind first, you can potentially degrade performance and introduce surprising behavior in your code. In C++11, some new utilities were introduced to replace the deprecated utilities that I just mentioned. std memfun, as an example, or std bind, all replace the versions of memfun or bind first, bind second that I've shown you before. Weirdly enough, for various reasons, even though they were introduced in C++11, they're actually inferior to lambdas and they should be avoided. Stephen T. Lavoie, principal developer on the Visual Studio C++ libraries, gave an excellent talk at CPPCon 2015. Functional: What's New and Proper Usage. In this talk, he explains the shortcomings of the aforementioned standard library functions in depth. I strongly encourage you to watch this talk if you're interested in the technical details. Here's a screenshot from the talk. It says that memfun isn't really fun. The good thing about it is that it's usually terse, but is very resistant to optimization as the compiler cannot transparently see through it, and in some situations it won't actually compile. As an example, if you have overloaded member functions or templated member functions, you still need to disambiguate using static cast as seen in some of the previous slides. Unnecessarily, it also fails when member functions have default arguments, and there is really no workaround for it. His recommendations are to avoid using memfun and use lambdas, especially generic lambdas. Even though they're slightly more verbose, they optimize away and they always compile and don't have ambiguity issues. It also covers problems of std bind. It has all the same issues in terms of performance as memfun, also with function pointers in addition to pointers to member functions or member data members. It also might emit very, very long and hard to read compiler errors if you misuse it. The syntax is also quite weird compared to normal C++, as you have to use these std placeholder objects, and it gets really tricky when you have nested binds. There is no short-circuiting for logical AND or logical OR, which might surprise you and might actually affect the semantics of your code. And sometimes you might have surprising behavior because the bound arguments are passed at L values. In this case, if you try to pass a unique pointer through bind, it might be surprising that it doesn't get moved and you cannot control it. There also are other surprising behaviors that can happen when you have some bind that's delaying a call under the hood, or sometimes placeholders and nested binds can actually invoke move operations twice under the hood. Again, his recommendations are to avoid using bind, even though it was introduced in C++11, and actually use lambdas, especially generic lambdas. He says that bind was a good idea in 2005, but is now a bad idea in 2015, because we now have language support to express binding arguments in a way that's transparent to the compiler and doesn't have any gotcha or surprising behavior. I agree with all of Steven's recommendations, and I strongly encourage you to follow them. Let's now see how you can replace std memfun with lambda expressions. So given a member function pointer, std memfun returns a call wrapper of some unspecified type that can be invoked. In this case, imagine that we have a struct called foo, which contains a print member function that just prints one of its data members. Now we can say auto fooprint equals std memfun of the address of fooprint, and what this will do is create this new fooprint wrapper that can be invoked with an instance of foo, and it will automatically call the print member function on the provided instance for us. This is useful when you want to have some sort of call wrapper for a member function, but you don't actually have an instance to call the member function upon. So you simply say that fooprint will call print on any provided instance of foo. Like std bind and function pointers, it unfortunately fails on overloads and templates. So if your foo struct actually provides two overloads of print, using memfun will give you an error about matching function for call to memfun. This is because the compiler is not able to resolve the overload by simply taking the address of fooprint. It requires an explicit disambiguation using a static cast. Let's now see how you can achieve the same behavior by using a lambda. Note that using a lambda here is a zero-cost abstraction that seamlessly works with overload and templates and allows the compiler to aggressively inline and optimize. In this case, I'm simply creating a variable called fooprint and initializing it from a lambda expression that takes a thisFoo by autorefref and then invokes print on the taken thisFoo. So the intended usage is that fooprint given a foo instance will call print on the foo instance. And this is exactly what memfun does for us, but expressed through a language construct which is transparent to the compiler and doesn't have any surprising behavior. Please note that this version will work with the previous struct foo definition seen here, as using this foo.print will automatically do overload resolution for you. Let's now see how lambda expressions compare to stdbind. The behavior of stdbind is as follows. Given a function object f and some arguments, stdbind returns a call wrapper of some unspecified type equivalent to invoking f with some of these arguments bound. In this case, I have an int add function that takes two integers and returns their sum. And I can say something like auto add 10 equals stdbind of add 10 and std placeholders of 1. This line means I want add 10 to be a wrapper around the add function where the first argument is fixed to 10 and the second argument is a placeholder that the user can pass arguments to. So if I try to stream out add 10 invoked with 10, what will happen is that the add function will be called with 10 as the first argument as provided by the fixed bound 10 argument, and 10 as the second argument, which is provided by the user. This will go through the placeholder, and in this case it will print out 20 as I'm summing 10 plus 10. Let's now see the usual issue with overloads. Let's assume that I want to provide an add for integers and an add for floats, so I have two different overloads. If I try to bind add with 10, I will get an error that tells me that it wasn't able to resolve the overload. I will get an error that tells me that there is no matching function call to bind, as the compiler wasn't able to resolve the overloaded function type. Again, this requires a static cast. Using a lambda here is again a zero-cost abstraction which works with overloads and templates, and it's even more readable than bind. In this case, all I have to say is auto add 10 equals some lambda expressions that takes an int and returns add of 10 and that int I was just passed. As you can see, this is easier to read as it's regular C++ syntax. It shows that you're binding 10 as the first argument of the add call and having some placeholder x as the second one, and it works with any kind of overloaded template and can be very aggressively optimized and inlined by the compiler. As you can see, this is how you could write a generic add 10 wrapper that works with both the int and float overloads we've seen before. We're gonna take an auto x as our argument, and we want to make sure that it's casted to the correct type. So if we take an int as an argument to the lambda, then we want to invoke add with an int and an int. If we take a float as the argument of our lambda, then we want to invoke add as a float and a float. So in this case, we need to static cast our 10 literal to the correct type to avoid ambiguity with the overloads. But this works properly and is again completely transparent to the compiler. Here's a recap of this video. Closures produced by lambda expressions are first-class citizens. This means that they can be assigned to variables, copied, moved, passed around, etc. Many functional utilities have been deprecated in C++11 and completely removed in C++17. Lambda expressions can be used instead. Also, utilities such as memfun and bind, which were introduced in 11, shouldn't be used anymore. Lambda expressions are superior to them for a plethora of reasons. So far we dealt mostly with local lambda expressions. But what if you want to store them or store any generic callable object?